Morning, everybody, and thank you for inviting me here in this fantastic place. It's very amazing faculty and part of the world to be, I think. So thanks, Luis, for inviting me. So today I'd like to present this ongoing work. So this is not something is done. It's something that I'm doing currently, and it's a numerical study of very complicated system of point vortices with the background smooth vorticity on a sphere. So the complication is that point vortices are delta Dirac functions, and the background vortice is smooth. So there is a complete different nature of these two objects. But in some models, they're coupled together, and they form an interesting example or an interesting model for oceanic and atmospheric dynamics. So this is the outline of the talk. I will exactly explain why this might be an interesting research topic, and then I will present the Euler equation on a rotating sphere and the couple model established in literature, and then I will present my work, so the discretization for applying a numerical method, and then I will end with talking about relative equilibria in this case, and what we can say about relative equilibria when we have this coupled system of singular vorticity and smooth vorticity. So as I said, the main interest in application is atmospheric and oceanic dynamics. The coupled system model is necessarily introduced when the sphere is rotating. So for modeling atmospheric and oceanic dynamics in reality, it's necessary to take into account the rotation of the Earth. And when the Earth is rotating, the coupled model between point vortices and smooth vortices is something that has to be taken by physical reasons and by mathematical reasons, if you want. So we will see why this is necessary. So what is missing in numerics is a structure preserving numerical schemes. So the Euler equations, as you know, have a big geometrical structure. Like they present a lot of symmetries, and they can be seen as a Lipposon system on the dual of the divergence theory vector fields. But no numerical methods have been built to preserve this structure in the discrete setting. And last but not least, the dynamics and the classification of the relative equilibria configurations of the point vortices when there is this coupled system with the background vorticity are not still completely known and classified. Okay, so let's start with the Euler equation on the rotating sphere. Let's say what we are talking about. And so our space will be this STF star, so the dual, as I said, of the divergence-free vector fields on the sphere, on the two-sphere. And I defined this infinity 0. So the 0 here is because I want smooth function on the sphere that have 0 integral, okay? It's not related to the compact of the functions. And the Euler equations I looked at are those of the vorticity, and they are presented in this form, where these are the canonical brackets on the sphere. And so omega is our vorticity, and F represents the rotation of the sphere, and is called Coriolis force, or represents the Coriolis force. The Hamiltonian of the system is this Hamiltonian here, where this is the inverse of the Laplace-Beltrami operator on the sphere, and the inverse is well defined because the kernel of the Laplace operator are just the constant functions. So everything is good here. But now, if we want to have point vortices in our model, we have to extend our dual space to a space of distributions that integrate to 0. So this famous paper mentioned yesterday by Tudor, Ratio, of Marsden and Weinstein in 1983 proved the existence of finite dimensional coadjoint orbits of the Euler equations that are called point vortices. And this is a classical expression for this point vortices. So we have the strength of each vortex, then the Dirac delta function here, where xi is the position of the vortex, and then we have this constant here that puts the integral of the vortices to 0. The coupled system was introduced first by Bogomolov in 1977, And he does the following splitting of singular vortices and smooth background vorticity. Okay, so I say restriction because we don't take the whole distribution space, but we take this kind of subspace of distribution space, which is invariant under the Euler equation. So if we start in this space, we stay in this space. So the splitting is, and the Euler equation are well posed on this splitting. So what we have is a Lipposon Hamiltonian system on R3 and V, where NV is the number of vortices, and S infinity 0 S2. The Hamiltonian is this complicated function. So here we see the classical Hamiltonian for the point vortices. Here we see the couple part of the Hamiltonian. And here we see the smooth vorticity part of the Hamiltonian. The equations of motions are in this, given by this form. And here I want to stress again the coupling in both equations, here, sorry, and here. Okay. The thing that I want to stress for, which is important for applications and not only, is that this logarithm presents a bad singularity here. So we regularize the logarithm just replacing this singularity with a non-singular logarithm, adding a small epsilon here. This won't affect the dynamics too much, especially in the application. So this is where the exact the theory ends, more or less, about this infinite-dimensional space. And now we want to move to the discretized system. So how do we discretize this system? Sorry, I forgot this slide. So very important, this system presents several first integrals. One is the Hamiltonian. Then we have the momenta of the vorticity. And then we have this other moment function, which reduce to just a z component if we take the vorticity, the rotation of the sphere on the z direction. So instead of having 3 conserved quantities, we have just 1 conserved quantity. Okay, so discretization. The geometric point of view of discretizing the Euler equation was first studied by Hoppe in 1982 in his PhD thesis, and he found, or he showed that C infinity 0, so these functions are an L alpha limit of SUN as n goes to infinity. This is a special result of a much larger theory of geometric quantizations and the theory of deformation of Poisson brackets. So in a precise sense, we can say that this finite dimensional Lie algebra approximates this infinite dimensional Lie algebra. It's enough to say for today that if we specify a basis of this, a special basis of this algebra, and a special basis of this algebra, we get that the specific structure constants converge pointwise. Okay, so this is not canonical at all. It's important also to know that's a non-canonical approximation. So what we do here, we have our smooth vorticity and we express in spherical harmonics, and then the spherical harmonics are replaced by a special basis, which is called spherical matrices of SUN. So what we have now is a Lipposon system on R3 and V and SUN for n as large as one wish, and the larger, of course, the better the approximation is. And the brackets are the usual commutator of matrices scaled by a factor which is n to the power 3.5. The Hamiltonian, the discrete Hamiltonian that I propose is this one, okay, which is exactly analogous to the continuous one. And here we have the coupled part, which of course is truncated to the level of SUN we take. And these are the equivalent equations, or equation of motions in this finite dimensional space. Okay, and again we have the coupled system here.
What is the COR?
Sorry?
The COR.
Sorry, yeah, COR is the Coriolis matrix, or correspond to the Coriolis force. Thank you. And so what is nice of this system compared to other numerical approximations, and I think it might be appreciated by geometers, is that this system has a lot of discrete first integrals that completely resemble the infinite-dimensional case. So the Hamiltonian is a first integral of the system. Then we have the momenta of the vorticity, which is now a matrix now, for n equals 2 to nv. Sorry, this is a mistake. This is n big N, not net v. And this momenta, which is exactly the same we saw before, instead of having an integral here, we have a projection on these matrices that represent the directions. Okay, so we have exactly the same bunch of integrals that are large as we take n large. Okay. So now we've seen just the spatial discretization, and to solve our PDE, we need a time discretization. So we have an Lipposon system on R3, and the coadjoint orbits of this Lipposon system are products of spheres. Okay, so we know in literature this is the best numerical scheme to solve Lipposon system on R3, or products of sphere, which is called Spherical Midpoint, and was found in 2013 by McLachlan, Modin, and Bergier. And Klaas Modin is my supervisor. And this year we found out an analogous scheme for SUN to apply to the global system. And these two methods applied together will provide a Lipposon integrator on the global system. Okay, so the idea is to use something is known as collective integrators. So collective integrators rely on the construction of a collective Hamiltonian on a linear space, possibly, so that on a linear space we apply a numerical method, and then using a momentum map we managed to create a numerical scheme, a map descended to the Lipposon space. So in more detail, what is needed is this identification of the algebra with a dual via the Frobenius norm. And then we take the Hamiltonian action of SU2n V and GLNC on this space. So C2 and V and T star GL and C. Okay, why? Now it's a bit confusing because I was talking about SUN and now I'm talking about GLN. So the thing about GLN is that the momentum map is much easier to analyze, and we derive a much simpler numerical scheme using the cotangent lifted action of GLN on its tangent bundle. So we will see that it's enough to study Lipposon systems on GLN star and having quadratic preserving numerical schemes to derive a numerical scheme here. Okay, so somehow aiming for the simplicity gave a better result in the end. So we have this momentum map, equivalent momentum map here, and with 3 will extend the Hamiltonian to the orthogonal complement of SUN star. And as I said, we use the momentum map to lift the equations from here to here, and this will give us a collective Hamiltonian. We apply on this space, on the bigger space here, we apply the classical implicit midpoint rule, which is a symplectic integrator. Okay, and then using the fact that the momentum map is a Poisson map, we derive a Lipposon integrator here. And since the midpoint rule preserves quadratic first integrals, we found out that the Lipposon the same method can be used for Lipposon system on SUN star, or even more general algebras, but for us it's enough. So the final map of this process will end up as a Lipposon integrator on the latter space. So this is the first theorem about the spherical midpoint, which says what I basically told you. So when you get the collective Hamiltonian and you apply the midpoint on C2 and V, then you will end up with the spherical midpoint method on R3, which preserves exactly the coadjoint orbits that are the two spheres. And the map is completely explicit. It's here. Okay, so this is straightforward. And the same result we got for SUN, but working a bit differently. So instead of working with the action of SUN on some space, we work with the action of GLN. Okay, and we found out an explicit method for SUN, which is this, very simple also. So we have just two unknown matrices here. Okay, the last line is explicit. So why, and yeah, so this is the global result. So we, these two methods applied together are a Lipposon integrator on R3 NV SUN star. This is because more or less, morally what we are doing is that we have a numerical method here, and then we change coordinates in a different way, right? In a way, we change coordinates with the momentum map ended up in R3, and in the other, we change coordinates ended up in SUN. So more or less just a nice change of coordinates. So the properties of this global method is that it is intrinsically defined here. So there is no round-off error about the method. So the computer exactly stays in this spaces. It's a Lipposon on this space. So we have near conservation of the Hamiltonian, which is ordered to the h-2. H is the time step. And round-off precision of the conservation of the discrete Casimirs. Okay? And the method is SU-NV-SUN equivariant. So it has nice equivariant properties. It's second order accurate in time, second order accurate in space. This is due to the quantization deformation of the brackets. Okay, so now it's time to talk about relative equilibrium. So here just recall a relative equilibria. So given the Hamiltonian system with symmetry group G, we say that a point is relative equilibrium if there exists a one-parameter subgroup such that the flow starting at this point is exactly parameterized by this one-parameter subgroup. In our case, the group of symmetry is SU2 because the sphere is spinning, right? So we search for relative equilibria that have this symmetry, that are related to this symmetry. And in general, what we expect is that interaction between background vorticity and endpoint vortices destroys non-rotating equilibria. Okay, so if you have an equilibria of point vortices on the sphere, it's likely that if you make the sphere rotate, this equilibrium is completely destroyed, right? But is it possible that some stable non-rotating equilibria don't drift too far away from the initial position when the sphere is rotating? So James Montaldi worked, and other collaborators or students of him work a lot on equilibria of point vortices. And they have a lot of results for the non-rotating case. And I wanted to try just one simple case. And I must say that here is where my work has arrived. So I would really appreciate any suggestion or, let's say, comment and contribution to this part, because now it's where the method should be applied to see, to have an idea how the relative equilibrium evolves when you have the rotating sphere and the coupled system. His student, Laurent Paul, also worked on the coupled system, but he has some conjectures on the equilibrium eventually. So I tried this system here of 6 identical vortices equally spaced on a latitudinal circle, and the result of Laurent Paul, Montaldi, and Roberts is that this equilibrium is Lyapunov stable if this condition holds, where theta 0 is the colatitude of the longitudinal or the latitudinal circle of vortices, and linear unstable if the inequality is reversed. So now I have a small animation for this. So this animation was made with the background vorticity with initial condition, which is Coriolis vorticity. So you see these colors, that is the strength of the vorticity. So the closer you are to the poles, the stronger the vorticity is. And these point vortices have the same strength, and they are equally spaced on the more or less on the equator here.
So let me understand. The colors are related to the background omega,
yes.
or are they related to the Coriolis force?
No, they are related to the background omega,
Okay.
which as an initial value I give the Coriolis force.
Okay.
So it's a standard initial value you can take. Yeah, you see a bit of. So here there is some different colors because this is the first iteration. It's not the 0 iteration. Anyway.
So without the background, this is unstable.
Yes, exactly. So this is on SU n for n equals 51. So the definition is not too high. To have very nice definition is enough to have n equals. It's at least we require at least to have n equals 200 and something. In other simulations, you can go with SU 1000 or something. So here the equilibrium is unstable, but not terribly unstable. So you can move a bit farther to see what happens. Oh, sorry, a bit too much. Okay, so here the vortices are moving, and at a certain point the equilibrium is going to be broken. Let's see. So now you see that they are lifting the lines and they swap. Okay. So they have this nice behavior here of swapping. And this swapping will continue for a while until they even drift too much and the system becomes more or less chaotic. It's a bit slow, the video, but. And now I don't have, we don't have much time, but also I tried also to invert the relation, so to take an angle where we have a stable orbit and so if I take, for example, the vortice is equally spaced up here, so closer to the North Pole, they don't move from there, they are very stable. So it seems that what we have, and maybe we can stop here the animation. So here is just to see the Hamiltonian variation. It's very small. So this is minus 14. So it's round off precision. This is the Hamiltonian considered to minus 3. So the conjecture I wanted to address you is this. So a stable SU2 relative equilibrium of point vortices persists when the sphere is rotating, whereas the background vortice does not need to be in a relative equilibrium. So the relative equilibrium of the point vortices remains when the sphere is rotating, but the background vorticity is completely influenced by the vortices, and so it's not in an SO2 relative equilibrium. Okay, that's my conjecture. And then, well, this is something. So two inverse polar vortices on the two poles with the Coriolis initial smooth vorticity is the only. Well, this is not okay. This is cancel this. This is wrong. But I also wanted to say is that to have a full equilibrium of point vortices and global vorticity, we need that the vortices have to be on the poles. Otherwise, we always see an interaction of point vortices and the global vorticity. Okay, and the initial vorticity has to be symmetric with respect to the rotation. So Coriolis or other spherical symmetric initial data. Okay, and yeah, so that's all. Thanks for your attention.
Questions, comments?
Yes?
So when you showed us the explicit integrator, it looked very simple. And I was surprised Because these structure constants are very complicated, right? These Wigner 3J symbols, so why are they not there?
You mean in the one of SUN? Here?
Yeah, exactly.
Yeah, so here, the question is why it's so simple.
Yeah,
So-
particularly I mean, I know that the structure constants on the algebra are complicated, but why do the structure constants not appear?
Because what they do is to take the original system and I lift it to Hamilton equations on the canonical Hamilton equation on T star GLN. And then I applied a midpoint rule, so I get a numerical, a discrete evolution there. And then playing around with the variables there, you get like let's say another discrete flow in these variables, and so you don't need to take into account the structured constants, because when you have a Lippershorn system in GLN star, okay, the expression of the if you write the Lie brackets is the same. So for GLN star you always have, and you use the Frobenius norm to identify the dual. You always have this kind of equation. So it's just a matrix commutator here. And the structure constants are encoded in the commutator of matrices. You don't have to specify them. And when your Hamiltonian is, the gradient of your Hamiltonian is in SUN, with this method, because of this quadratic conservation of the implicit midpoint rule, will stay in SUN. So you don't have to specify any structure constant, because the structure constants are already encoded in the matrix multiplication. It's just, what people think is difficult, like for a computer now, is to solve this system. It is an implicit system, right? So you see that X and K are implicit at that time. So if you want to say about this principle of conservation of the difficulty, the conservation of difficulty here is, okay, I have large matrices to multiply to find what these X and K are, okay? But the structure constants are encoded here in the multiplication of the matrices. This is the moral answer, I can say.
The fluid mechanics people say that when you have a small amount of dissipation, there will be a tendency of the homogeneous part of the body to spread and become uniform.
Mm-hmm.
In your model, you're not adding dissipation at all.
Yes.
Very conservative.
Yes.
In your observations of the experiments, we saw a little bit of blending of the colors.
Mm-hmm.
As you go on and on and on, would you expect that it also becomes sort of a mixed blur of color, or they will keep like patches of different colors?
Okay, so
different vorticities.
yes, I can answer you in this way. So this this method here works very well, even if you don't have point vortices, right?
Yeah.
So there was a paper of Dritschel recently, and also Paul Newton addressed like a question: what is the destiny of long time simulations of vortices or random initial data on a sphere, for example? And applying this, so Dritschel and his co-authors found out that for a random initial vorticity, they found that 4 large big vortices, for their initial vorticity, 4 large big vortices persisted. So it's not 100% sure that the total vorticity just become a complete mix. There are some big vortices, in that case 4 vortices, that are stable. And because of the conservation laws, so because of all this infinite number of Casimir, these big vortices are enforced to stay stable. So there's not this ultraviolet catastrophe, right? It's not that everything is dissipated in the low frequencies of the spherical harmonics. These big vortices, some of them persist. And applying this method to their initial vorticity, I found also 4 big vortices that persist. So it seems that this nature of having big vortices that persist in time is respected even when we discretize with this quantized approximation. So I don't expect that the total vorticity will disappear in a complete blend of colors.
Any other comments? Let's thank the speaker again.